2.6, which is about limits at infinity. So we're going to be taking the limits as x goes to positive and negative infinity in this lesson. Just a quick note that's highlighted here as before we start. Infinity and negative infinity are not actual numbers. They represent values of x that increase or decrease without bound. So you can't actually take the value of a function at infinity, but you can take the limit as x approaches infinity. So the definition here, if we take the limit as x goes to infinity, we're talking about what's happening to the function as x gets larger and larger and larger. And similarly with x approaching negative infinity, we're looking at values of x that become larger and larger and larger, but negative. Okay, so we're going to look at some examples. Just going to get my pen here. So in this case here, we see that as x becomes larger and larger and larger, the function is approaching y equals L. So we would say in this case that the limit as x goes to infinity of f of x is L. And finding limits at infinity also helps you find horizontal asymptotes. This is also a horizontal, H is for horizontal, asymptote. Okay. In the next scenario 2, we see that the function is oscillating about this y equals L line, and it's approaching it. These oscillations are getting smaller and smaller and smaller. So it's also a horizontal asymptote, and this is another case where x approaches infinity. The function approaches L. Change here to write that this is another horizontal asymptote. Okay. The third scenario here is showing an example where x is approaching negative infinity. So as x gets large but negative, we see the function approaching y equals L. So in this case, the limit as x goes to negative infinity would be L. And again, this is horizontal asymptote. So what if we didn't have the graph? Let's do an example where we use a table. So let's look at the function x squared minus 1 over x squared plus 1. And we're interested in finding the limit as x goes to negative infinity. So what we do here is we just plug in larger and larger negative numbers. So negative 10, negative 100, negative 1,000. I'll start with those three, and we're going to plug them into the function and see what we get. So you can just take my word for it, or you can do it yourself too to prove it. 0.98 is what you get when you plug in negative 10. 0.9998, and then 0. There's 5 nines. 1, 2, 3, 4, 5. 0.999998. So I think you can stop there. You don't have to fill out the whole table as long as you can show that it's approaching a number. So here we see that the function is approaching 1. It's getting very, very, very close to the value of 1. Of course, it's never going to actually reach 1 because you can never actually plug in negative infinity. So we say that the limit as x approaches negative infinity, x squared minus 1 over x squared plus 1 equals 1. Okay. And let's have a look at the graph. It's shown down here, and we can see this is true. It actually approaches 1 on positive as x goes to positive infinity and negative infinity, and 1 is a horizontal asymptote. Okay, let's do some examples. Let's do another example. Let's look at x 1 over x as x approaches infinity and negative infinity. Okay, I'm going to just split the page in half and do one on either side. Okay, so we're going to make a table, and we'll plug in, we'll go positive infinity first, so we'll plug in 10, 100, 1,000, that should be enough. Second. Okay. And when you plug that into f of x, 0.1, 0.01, 0.001, right? Dividing by a large number makes a very small number. So we can see that we're approaching 0. So the limit as x goes to infinity of the function equals 0. Okay, let's look at negative infinity. Negative 100, negative 1,000. So 1 divided by negative 10 is negative 0.1, negative 0.01, negative 0.001. Okay, so it doesn't matter if you divide by a large positive or large negative number. 1 divided by a large number, whether it be positive or negative, is going to be very close to 0. So limit as x goes to negative infinity, x is also 0. Okay. So the function would have a horizontal asymptote at x equals 0 also. All right. Let's do some examples where we're not making a table. We're just doing it by what we know about dividing by large numbers. Okay, so next question here, limit as x goes to infinity of 1 over x cubed. So just like we saw with 1 over x, if we're going to be dividing by larger and larger numbers, we're going to get a very small number close to 0. So 1 divided by larger and larger numbers is going to approach 0. So I'll write that in the explanation below. So dividing by successively larger numbers smaller numbers that approach 0. Okay, let's look at the next example. Even though it looks more complicated than A, the same idea applies. So you have 1 divided by a very large number times a very large number. So it's going to be very small. So it's going to approach 0. Same concept as in the next question here. This one is more complicated. So we have a rational function 2x squared minus x minus 1 in the numerator, and then 4x squared plus 7 in the denominator. So when we're looking at very large numbers, we can just consider which terms are going to dominate. Like when you have a large number and you square it, it's going to be much bigger than just the x term or the 1 term. And then same in the denominator, 4x squared is going to be way bigger than positive 7. So when we're looking at the limits, we can just look at the dominant terms. These numbers are going to be much, much, much larger than the other terms in the equation. So what we do is we take the dominant term in the numerator and the dominant term in the denominator and just consider those. So this is going to be the same as the limit as x approaches negative infinity of 2x squared, 4x squared. And we see a cancellation happening here. The x squared in the numerator and in the denominator. And so we have the limit as x approaches negative infinity of 2 over 4, which is 1/2. So in this case, there would be a horizontal asymptote at 1/2. And so I'll write this down below as well. As x goes to infinity, we only need to consider the dominant terms or I guess we're going to negative infinity here. We only need to consider the dominant terms in the numerator and denominator. So in this case, the degree of the numerator was the same as the degree of the denominator. They both have an x squared term, and so those are going to cancel out, and we're going to get a non-zero answer. In the next question, we have a degree 4 term in the numerator and a degree 3 term in the denominator. So the degree of the numerator is larger than the denominator. We haven't done this type of case yet. I'm just going to highlight the dominant terms and look at those only. This is the same as limit t goes to infinity, 7t to the power of 4 over 2t to the power of 3. And we do have some cancellations. We have t cubed, we fully canceled in the numerator, and we'll take away 3 t's in the numerator, and we will be left with limit t goes to infinity, 7t over 2. Now we have to look at that. So we can't plug infinity directly in here. 7 times infinity divided by 2 is not an actual number. However, as we plug in larger and larger numbers, we can see that this is going to grow and grow and grow. It's going to get larger and larger and larger. If I plug in 10, it'll be 70 divided by 2. And if I plug in 100, it'll be 700 divided by 2. So it's going to get larger and larger and larger. So this is going to grow and grow and grow. So this is going to be infinity. So in the actual function, when you draw it, the arrow is going to go upwards at the end of the function. So there's no horizontal asymptote in this case. Okay, and the last one, again, it's similar to part D. I'm just going to highlight the dominant terms. And notice in the denominator, you have to keep the sign in front of the dominant term as well. And so this would be the same as limit x goes to infinity, x squared over negative x. So we see again the degree of the numerator is larger than the denominator. We can make a cancellation. So this is the same as x goes to infinity of x over negative 1 or negative x. So this is going to grow and grow and grow, except it's going to be negative. So it would be negative infinity. Okay, so we're just going to go back through those again and just sort of make a little rule for each case. Okay, so in the first two, we see that the degree of the denominator is the degree of the denominator is greater than the degree of the numerator. In both of these cases, the result was we had 0 as our answer because dividing by larger numbers makes smaller and smaller numbers. So let's just write that on the side. So degree of numerator is less than degree of denominator, and therefore we get 0 because we end up dividing by larger and larger numbers. In this case here, we had the degree of the numerator and denominator being equal. Therefore, we got a horizontal asymptote, but it was not at 0. So this case, we had degree of numerator equals degree of denominator. I'll write non-zero asymptote, horizontal asymptote. Okay, and then the last case was where the numerator had a larger degree than the denominator, and both of those cases we had either positive or negative infinity being the answer and no horizontal asymptote. So the degree of the numerator was larger than the degree of the denominator. Therefore, the answer was infinity or negative infinity and no horizontal asymptote. And so your assignment is listed there. Again, actually, yeah, I forgot to change this. So in class means those are the required questions, and then the at-home questions are the ones that are optional if you feel like you need extra practice. Okay, that is it for lesson 2.6.